Okay, so one of the methods under the geometric method in determining the deflection of beams is the double integration method. So this is the first method that I'm going to introduce. So before we start with the computation, I'm going to derive first the equation. So as you can see here, we have the equation for the slope as the integral of m over ei dx, and the deflection denoted by y as the double integral of m over ei dx squared. So to start with, let's have here an image, no? So we have here a beam, and then the yellow line is what we call your elastic curve, or the shape of the beam once it deflects. So kasi, as you can see here, no, about any point along the beam, no, nagva-vary yung ating deflection. So it is important that we know how to solve for your deflection. So yung double integration method kasi, this is a method wherein we can derive a general equation in terms of an arbitrary distance x. So once we arrive with a general equation, we can actually solve for the deflection about any point along the beam just by substituting the value of x on that point. So for example, kung gusto kong malaman yung x dito sa, yung deflection dito sa gitna, all I need to do is use the distance L over 2 dun sa equation na madiderive natin later on. But again, to start, let's have this figure. Now I'm going to derive this equation, theta, for the slope and then deflection. So let's start first with, let's have draw tayo ng tangent line dito sa point y. So draw tayo ng tangent line. And so if this is the tangent line, so of course this will have a angle theta, and then you have your dy, and then of course distance dx. Then using the tangent function, we can just write here tangent theta is equal to dy over dx. So for us to have another equation, actually kasi ang slope natin, or rather the deflection on a beam, the value of the deflection is relatively small, especially the slope, no? Hindi siya yung napakalalaking value. So most probably yung makukuha nating angles is just 5 degrees, 10 degrees, etc. Now, an angle that is small is actually just equal to tangent theta. Pwede nating sabihin na tangent theta is just equivalent to your theta. For example, say, example tuloy tayo para pakita natin. So if you have a theta that is equal to 5, say, gawin natin 10 degrees, no? So, just get the calculator. So, 10 degrees. So, if i-convert ko yan into radians, di ba, magiging 10 degrees times pi over 180 degrees. So, that will be equal to 10 times pi divided by 180. So, that's equal to 0.1745. So, that's the equivalent value. Try naman natin yung tangent theta. Tangent theta, or tangent 10, is equal to, so again, I'm just going to use the calculator. Tangent 10 is also equal to 0.17. So as you can see, the value of the two angles is equal. So this, we can actually say the tangent theta is equal to theta. So having said that, we can just rewrite this one here as theta is equal to dy over dx. Now, based on this equation, no, ang hinahanap natin, no, what we're looking for is the deflection or the distance from the point or the original point to the deflected shape. So it should be in terms of y. So I'm going to rewrite this now in terms of y. So magiging siyang dy is equal to theta dx. Then rewriting this one in terms of your y. So I'm going to just integrate it na para maging y siya. So rewriting, we will have y is equal to the integral of theta dx. Okay, so now we have an equation, pero in terms of theta siya. So what we want is an equation in terms of moment. So, meron tayong ibig sabihin dito, no? The deflection daw is equal to the first integral of the slope or the angle. So, to have another equation, i-relate natin yung theta to bending moment. No? So, I'm going to write here, we need to relate the slope of theta to the bending moment. Now, so to do that, I'm going to explain first the behavior of a beam once it is subjected to bending. So, for example, pag magbe-bend po ang beam, kunyari ito na. Yan. So, magbe-bend siya. Ay, sorry. Naka-auto pala. So, if the beam is subjected to bending, pag meron tayong bending moment sa beam, this surface here at the top actually tawag dyan is being compressed, no? Tapos yung nasa bottom naman na part is being stretched. Di ba? Kasi ang from this shape, you know, so mag-undergo siya ng bending na ganun. So mag-iiba po yung length. The top part of the beam will undergo compression, and then the bottom part of the beam will undergo tension. So lagyan natin, no, para may label. So sorry. So we'll have here, say, this is the top part here. We're going to call it as your compression zone. No? Compression zone, ibig sabihin po, na-compress siya. No? Na-compress or umikli yung fibers. And then, dito naman sa bottom part nung ating beam, na-stretch naman siya ngayon. So, this is what we're going to call it your tension zone. Wherein, na-stretch. Na-stretch yung portion. Pero, actually kasi, if you'll notice here, the fibers on the beam varies or yung nangyayaring compression dun po sa beam natin varies siya fiber to fiber. So para mas ma-explain natin, say, drawing tayo ng 3D. So, let's have it read the example. So if papansinin natin siya, no, the fibers, say for example, the fibers at the very top of this section is a lot shorter kung in comparison to, for example, sa portion ng ano na to, dito sa, sige, green natin. Ito, kunyari, sa portion na to, no, mas maikli po yung mga top fiber in comparison to this portion here. No? Kumbaga, ang nangyayari nating stretching and compressing varies from layer to layer. So, yung layer na tong pink is longer in comparison to this blue layer. No? So, yung layer na to, no, ito yung pinakamaikli or pinaka-na-compress na part. Yung pink na yan is yung just another layer. So, likewise, yung bottom part, ito yung pinaka-na-stretch na part, no? So, yung layer per layer, no? So, habang papunta tayo sa center, no, paikli ng no, pabago-bago. So, therefore, there's actually a portion on the beam wherein the original length of the member doesn't change. No? So, yun po yung tinatawag natin na yun yung tinatawag natin na neutral surface. Just do this first. So, gawa tayo ng so, meron tayong tinatawag na dito sa center niya, no? Meron tayo pong tinatawag na neutral surface. So, yung top portion natin, again, yung top part natin, itong ibabaw. This is the compression zone. Lahat to under compression, no? Or umiksi yung portion ng fiber. And yung nasa bottom naman natin is tension zone or nag-stretch yung fiber. Tapos, there's a area here wherein hindi nagbago yung fibers ng beam. Ito na po yun, Itong portion na to ng beam, ayan, yung nasa gitna, this is now what we call your neutral surface. So, or in this is what we call your neutral axis. So, kung titingnan natin yung dito, no? So, kung original length niya is x, no? So, ang length ng neutral axis natin will remain as x. Pero yung nasa compression zone, no? Yung value ng length niya, hindi na yun x. Since nag-compress na, nag-shorten, doon naman sa compression tension zone, nag-stretch naman or nag-lengthen yung original ng shape. So, having said that, so bakit siya importante? So, we need kasi to establish a mathematical relationship between the slope of the elastic curve and then the geometry of the deformed shape. So if we already know this principle, no, so we are going to correlate again the relationship between the slope of the elastic curve and then the geometry of the deformed beam. So, punta tayo dito. So, kung meron tayong dito kabla. So, ano na, I'm going to make a mathematical relationship between the slope and then the deformed shape or the geometry of the deformed shape of the beam. So, tuwa tayo ng beam. And then, let's have a, hindi may nasa gitna yun. Ah, so this is the x-axis. So let's say, kuha tayo ng portion na, no? Say this is your dx. Tapos, once na mag-bend yung beam, ganito yung magiging shape ng dx natin. Siyempre, nagbe-bend siya. So, let's say this is your so, label na natin. So, say this is your bs. S for the curve. Tapos, syempre, meron tayong tapos, we will have here d theta. This is naman the radius of curvature, no? R stands for radius of curvature. Now, if you recall, the equation for an arc length is equal to, gagamitin natin, no? So, ang formula po to get an arc length is equal to ds is equal to, or the arc length is equivalent to radius times the theta. Now, since, as we've mentioned, no, yung ds po natin, or this shape here, is along the neutral axis. Therefore, the length of your ds is just actually equal to your dx, or the original length. So we can just say, I'm going to write this one, I'm going to write this, dx is equal to r d theta. So i-rewrite natin siya naman ngayon in terms of d theta. So let's say in terms of d theta, so d theta na ngayon over dx is equal to 1 over r. Again, this is, how did we arrive at this one? This is basic algebra, no? So what we did is, dun yun sa, sorry, pupunta mo to sa ilalim, di ba? Ito naman dun sa, cross multiply lang siya. Kaya naging denominator both dx saka r. And then, we need to separate the d theta pala, sorry. Sige, i-write ko na lang ulit siya. So, mangyayari, just d theta is equal to 1 over r dx. And then, to get the slope, or the theta, integrate natin. So we have theta is equal to the first integral of 1 over r dx. But then again, what we want is an equation in terms of m. No, so ang meron sa atin is the radius of curvature. So to be able to get an equation, we have to understand the relationship of the bending moment and the radius of curvature. So as we know, no, sige, explain natin, no, the amount of deflection on a beam is actually directly proportional to the magnitude of the bending moment on the beam. Anong ibig kong sabihin? So, di ba? Kunyari, going to write here, draw here two beams, nag-deflect. So, say this is subjected to moment 1. Tapos, ito yung deflection niya. Y. Tapos, I'm going to draw another beam with a bigger moment. Siyempre, the bigger the moment, the bigger the bend is. The bigger the moment, the bigger the bend is. Sabihin natin, M2 naman to. Ay, sorry. M2. So, ito naman Y. So, as you can see, di ba, the bigger the moment, the bigger the value of the moment, no, the bigger the deflection is. So, i-compare mo, no, yung mas maliit yung moment, medyo maliit lang yung kanyang deflection. Nung lumaki na yung bending moment, syempre lumaki yung bending, so lumaki din yung deflection. So, we can say that the amount of deflection on the beam is directly proportional to the magnitude of the bending moment on the beam. In terms naman po of the radius of curvature, kasi yun yung kailangan natin. Ito. Yan. So, say, ito naman yung ating R1, then R2. Nice. Ito naman, baliktad naman siya ngayon. Now, the bigger the moment, the bigger the moment, the smaller the radius of curvature is. So we can say that the that the radius of curvature is reversely proportional to the magnitude of the bending moment of the beam. So if we are to write an equation in terms of this one, so pwede nating sabihin, no, na yung product ng bending moment natin and the radius of curvature will remain constant. Ibig sabihin na constant nag-change yung natin, radius of curvature tsaka yung ating bending moment. So we can write an equation, say your M1 R1 is equal to your M2 R2, no? Both of these will remain constant. So the constant value can actually be determined based on the geometry of the cross-section of the segment and the beam's material type. No, yung pagiging constant po ng ating value or ng beam, no? So the constant value can actually be determined based on the geometry of the cross-section of the shape. So kung cross-section ng shape ang tinutukoy, that is your moment of inertia. And then the beam's material type is actually what we call your modulus of elasticity. No, modulus of elasticity po is your based on the material type. So, pwede ko itong i-rewrite, no? So, gawin natin say MR is equal to EI. No? So, papalitan natin siya ng yung constant, papalitan ko siya ng neto, ng modulus of elasticity. Again, that's modulus of elasticity is based on the material type. So, what does that mean? For example, kung ang material po natin is steel, meron tayong value for that. Kung reinforced concrete siya, kung timber member, no? So, depende po sa material type. So, that is in terms of gigapascal or megapascal or pressure. And the I naman po, this was already introduced to you on your statics. So, I naman is based on the geometrical property of the beam. Di ba yung kunyari, etong portion na to na ito yung geometrical property ng cross-section. Now, to get the moment of inertia of a rectangle, di ba you have BH cube over 12? So, since we have this equation, and ang meron sa atin is this one, 1 over r, I'm going to rewrite this equation in terms of 1 over r. So, rewrite lang po natin siya. So, magiging 1 over r. Dapat separate eh. 1 over r is equal to m over e I. Okay? So, I'm going to copy this equation. So, we have, so copy natin. So, we have this equation. Ito yung original. Tapos, i-rewrite ko siya now. So, magiging siyang theta is equal to the integral of, sabi dyan, 1 over r is equal to m over ei. So, susulat ko siya ngayon dito. M over ei dx. Now, we will now go back to the equation that we derived here. Sabi dyan, your y theta dy is equal to your theta dx. So, going back here, no, kakopy ko naman yun dito. So, ito yung original equation natin. So, I'm going to rewrite this as y is equal to the integral of, ang theta natin is ito na. Ito yung value ng theta. Itong entire equation na to. So, I'm going to copy just that. So, mayroon tayong integral of m over ei dx and then the dx of the equation. No? So, ito po yung ating theta. No? Kinapi lang natin. So, ni-replace natin yung theta. So, there you have it. This is now your equation for your y. So, I'm going to write this in more simpler terms. So, the final equation is equal to y is equal to the double integral of your m over ei dx squared. This is also theta is equal to m over ei dx squared. So, there's your equation. Yan. Diba? So, there you have it. That is how we arrive with the equation on how to solve for your, the equation for the double integration method. Now, since I've already shown you how to solve for the, how this equation was derived, we'll now try to solve the deflection of beams using these equations.